In phase changes, we'll look at heating and cooling curves. The main reason we are doing this with intermolecular forces is because of what you already know about the states of matter. When we look at solids, liquids, and gases, there are some fundamental differences between how the particles are organized, the energy the particles have, and the forces or attractions that occur between them. So when we look at the primary differences between liquids and gases, it has to do with how close the particles are. Well, how close the particles are determines how great the interactions between molecules are. In other words, the role of intermolecular forces. Now remember, the intermolecular forces affect physical properties. Previously mentioned, these physical properties were the boiling and melting points, the vapor pressure, and the viscosity. Now, viscosity, you already know the basic definition, resistance to flow. So water and alcohol behave differently than something like molasses. Well, that difference is literally due to the intermolecular forces between the molecules, because in a liquid, what we're looking at is we're looking at that ease of motion. So how easily can they move past each other? If they can easily move past each other, well, then they have less viscosity because it's easy for them to move over and around each other. So if you spill water, alcohol, or honey, which one tends to stick around longer? This also plays a role into what we consider volatility, that ease of evaporation. So notice that increasing intermolecular forces increases viscosity, and increasing temperature decreases viscosity. And this ties back into what we know about how solids and liquids and gases differ from each other. So after viscosity, the next one we're going to discuss is surface tension. So surface tension is literally the ability to hold together, how attractive the particles are to the other particles around it. You see this if you put drops of water on a penny and how you get that bubble up over and around. This also plays a role in terms of adhesion and cohesion. Now remember, adhesion is the substance to a different thing. So for example, water onto the side of a graduated cylinder. Okay, that would be adhesion. Cohesion is any particle to itself. So cohesion is a direct result of the intermolecular forces that occur. So the more Velcro-like the particles are, the more intermolecular forces they experience, we see that increase in viscosity. We also see that increase in surface tension. And this plays out when you look at how particles behave climbing the graduated cylinder. This is why we have a meniscus. The particles are higher on the side with water than they are in the middle. Now, mercury, on the other hand, doesn't do that. Mercury has very little adhesion with a graduated cylinder, so it's actually convex instead of concave. And you can see this if you look at figure 1119. Now, getting to what we're discussing, and the point of this discussion being phase changes. Now in here, what you need to pay attention to is you need to pay attention to what exactly is considered endothermic and what exactly is considered exothermic, and recognizing really what's going on. So when we vaporize, when we sublime, when a substance melts, you're breaking bonds, you're disrupting those forces. It's sort of like you have to use more energy to push a heavy box on a floor than you do on ice because you're overcoming friction. So anytime you have to overcome a force, more energy is required. And this is why vaporization, sublimation, and melting and fusion require energy. They are energy absorbing processes. What's cool about this, and one of the things you want to recognize, is when we talk in this case, when we talk of phase change, okay, remember phase change is a physical property. It's a physical change in matter. Recognize that what we're breaking, what we're disrupting, that force we're disrupting is an intermolecular force, not intramolecular bonds. So a phase change is a direct, shall we say, a direct presentation of the amount of intermolecular forces having to be overcome, because the more energy required, the more the intermolecular forces you're having to overcome. The less energy, the fewer the forces. Now when you look at a heating curve, which is what we are traditionally used to seeing, where you have the solid Down here we have the liquid in the middle, we have the gas up top, and we're comparing heat to temperature. Notice how things change. Now again, remember that we said when we have an endothermic process, we're having to add energy to overcome the forces. What you want to recognize is that there's no kinetic energy change here. That means there's no temperature change. If there's no kinetic energy change in there, that implies what you're knowing right there is that we are overcoming the intermolecular forces in that particular phase of matter. So when we go from ice to liquid, we're overcoming the intermolecular attractions. When we go from a liquid to a gas, we're overcoming the intermolecular attractions, because what we're doing is we're forcing the particles further apart. And so in forcing them further apart, we have to overcome that attraction that exists between the particles. Now the other thing you want to look at is when you look at something like this, you can actually recreate this if you know temperature data and know that energy has to be added. So you can recreate these curves with a little bit of data. The other thing that we'll be discussing in the next section when we talk thermochemistry is you can actually do calculations associated with this information. So you can actually calculate the amount of energy it will require to heat liquid water from 0 degrees to 100 degrees. You can look at the actual amount of energy to go from water to steam right here, even though the kinetic energy is not changing. Now, a couple of other things you can get from the graph as well is if you look at, for example, the liquid water section, the steepness of the slope and the length of the slope gives you a little indication of the intermolecular forces occurring. So if we had to spread that slope a little to the right, that would tell you a little more heat's added. We already know a lot of energy is required simply to change the temperature. So you can look at those things and make some evaluations about the substance you're looking at. So when we talk about phase change, if we're going from the liquid to the gas, there are a couple of things we have to discuss. And the first one is, in essence, vapor pressure. So vapor pressure is what results from particles escaping the liquid and going into the space directly above it. So we have these particles escape and they occupy this space right above the liquid. Now, at any particular temperature, we have molecules escaping. We know this. In fact, they jump up, they come back down, they might get trapped back within the gas, within the liquid, and some other ones might escape, because in essence, since kinetic energy is an average, that means at the surface some of those particles of that liquid will have enough energy to escape, to become a vapor. Now, as the temperature rises, more and more of the liquid particles can escape, and this is what forms our vapor pressure. So we can see that occurring with increasing energy. Now, what's significant is that at a certain point, at a particular temperature, if we hold steady at a temperature, the vapor pressure and the liquid have what's known as a dynamic equilibrium. In other words, the rate of vaporization or evaporation at the surface is equal to the rate of condensation of, in other words, those vapors hitting the surface of the liquid and condensing back and becoming reabsorbed by the liquid. And so that rate of leaving and that rate of returning are equal. That's what creates what's known as our equilibrium. Now, the significance of vapor pressure and why we actually care about that rate is because the amount of vapor pressure above a liquid determines its boiling point. Because when the vapor pressure equals atmospheric pressure, then I'm at my boiling point. This is actually why altitude affects boiling points. So we know water should boil at 100 degrees Celsius, okay, when we're at sea level being 760 torr. And we're not at sea level, which is why water generally will boil at around 95 degrees Celsius. So this is also why when we had the liquid in the little syringe, when we decrease the pressure in the syringe, we could actually cause the water to boil at room temperature because of that effective pressure. Now, what's significant here is that this implies that we can condense a gas to form a liquid. But there is a certain point where that is not true. So even though traditionally, yes, that is one of the ways we can cause, for example, we can make carbon dioxide actually liquefy. We can make nitrogen liquefy. We can make oxygen liquefy. We can make all of our noble gases or hydrogen even liquefy with increased pressure. But there's a limit to that, and that limit is what's known as the critical. And at this critical temperature, no matter how much pressure I apply, the particles have way too much kinetic energy for any intermolecular force to be able to pull it back into the liquid. So no matter how strong the intermolecular force is, the particles literally have too much energy to be able to do that. And where we see this, or where this is most obviously present, is when we look at phase diagrams, where we see both solid, liquid, and gas together in one diagram. And it's diagrams like this where we can actually see what we know as sublimation and deposition. Now, a couple of important points is when you look at these, notice that we have changes in state along what these are known as curves. So we have the vaporization curve, we have the melting curve, we have the sublimation curve. And notice the direction that what it's called when we go from a solid to a gas, what it's called when we go from a gas to a solid, gas to liquid, etc. Now, the significance of each of these curves is that the curves represent the temperature and the pressure that melting or vaporizing or subliming will occur at each of those points. Now, again, when you look at this and we're looking at the states, notice that we have the critical point, okay, which is right here, and we have, and at this point, notice it stops, and we have what we call the supercritical liquid. In other words, you can't distinguish the liquid from the gas. And no matter how much pressure I apply, if I'm above this temperature, so if I'm past this temperature, no matter how much pressure I apply, I won't liquefy anything. But in essence, no matter what, at each point along this phase diagram, you can see the temperatures and pressures required to cause changes in state, cause solid, liquid, gas to exist at a particular set of conditions. Where it becomes significant is when we look at something like water versus carbon dioxide. Now, water and carbon dioxide have very different phase diagrams, and this has to do with a couple of points. First, notice here on this diagram they talk about the critical temperature and the critical pressure. Notice that it's really high for water as opposed to our example diagram. And the reason for this is because of the van der Waals forces, specifically the hydrogen bonding. So the greater the intermolecular forces particles have, the higher our critical temperature, the higher this critical point becomes. Now, in addition, when you look at water, we have this negative slope here. In other words, if you put on a rubber glove and you take ice and you squeeze it, you force the particles closer together, which means we actually cause ice to melt. So water is one of the only substances where increasing the pressure will cause it to melt, because it's one of the few substances where the solid is less dense than the liquid, and this is why. Now, carbon dioxide, on the other hand, typically tends to sublime because it takes a lot of pressure to actually cause it to liquefy.